Hello everyone, myself is Divya Bahal, Assistant Professor in Chemical Engineering Department at LG Institute of Engineering and Technology. The subject that I am going to take is Mass Transfer Operations 2. So moving with the lecture. In the last lecture of distillation chapter, we had an overview about vapor-liquid equilibrium. Now we will continue it. So the today's topic would start from phase rule. Okay, so phase rule has been studied in chemical engineering thermodynamics also. Let's have an overview of it. What does it state? See, the equilibrium in vapor and liquid system is governed by the phase rule. It is given as F is equal to C minus P plus 2, where your C represents number of components present and P is for number of phases. Okay. Now, here we are talking about binary mixture. Okay. For having a talk about vapor liquid equilibrium, we are starting with the binary mixture. So let's say that the number of components present are 2, whereas the number of phases which we will be dealing are liquid and phases. So P is equal to 2. Hence, solving this equation, F is equal to C minus P plus 2, that is 2. It means the degree of freedom is 2. Now what is the significance of it? So here, according to the phase rule, the degree of freedom or the number of intensive variables that must be fixed to define the equilibrium state of system are 2. See, the intensive variables are talking about. Intensive means which are independent of mass. Okay. So what are the variables that you have to fix? It is given to define this equilibrium state of system. So that from the solving the phase rule equation you get 2. It means you have to fix at least 2 of the intensive variables. Now in this system, which we are talking for the vapor liquid equilibria, you have 4 variables: pressure, temperature, liquid phase composition and vapor phase composition. So out of this 4, at least 2 of the variables has to be fixed. If these 2 variables are fixed, then altering any one of the remaining variable, the other variable would get satisfied automatically. For example, if I am fixing my pressure and temperature here, now if I vary my liquid phase composition, the vapor phase composition would be automatically will come in equilibrium with it and it will be defined. So that is the significance of phase rule. Now how it is applicable for VLE, we will see it further. Now here we are talking about a closed system. So note the point, first of all the discussion about a closed system. We are taking a mixture of benzene and toluene. Okay, we are taking a mixture of benzene and toluene. Now for this mixture, I am defining that my liquid phase composition of benzene is 0.4 and that of toluene is 0.6. Now I am defining here, it is actually given that benzene is more volatile than toluene. Okay. Now what is the meaning of more volatile? What you can relate? See, more volatile means it has low boiling point. The boiling point of benzene is about 80 degrees Celsius and that of toluene is 111 degrees Celsius. So you can see that benzene boils more fast than that of toluene. It has high vapor pressure. In last lecture we discussed about the definition of boiling point. Okay, it is related with the high vapor pressure. More the vapor pressure, it would signify that fastly it is satisfying the total pressure condition. It means fast high boiling point. Okay, low boiling point, sorry. And it is a light component. Now less volatile means it has high boiling point. Okay, and it has low vapor pressure and it is heavy component. Okay. So this way we are defining that I am taking a mixture of benzene and toluene, from which benzene is my more volatile. Now in a closed system, how we are starting our experiment, okay, for the VLE. See, in a closed system, that is initially at liquid phase, okay, I have defined the benzene and toluene composition as 0.4 and 0.6. Benzene is 0.4 and toluene is 0.6. Now it is a closed system. Okay. Now when I am heating it, the vaporization will start. Okay. Continuing my closed system condition on continuously heating, all the liquid will convert into vapor phase. But note down here, when all the liquid is converted into vapor phase, the initial concentration in which we took our mixture would be same. Now instead of liquid phase composition, I have vapor phase composition. Now you can see both vapor and toluene composition is 0.4 and 0.6. So we can say when totally in liquid phase and when in vapor phase, the mixture which we are taking, its composition is going to remain same. Now, when we are talking about purifying, see, in distillation, okay, in refinery you have seen, it is an open system, okay, you let out the vapor, you take out the vapor, and hence purity is increased. Here in closed system I am taking it. So for a closed system, when a liquid mixture is boiled, then vaporization takes place, okay. Here, because we are not allowing the escape of vapor, so all the liquid will vaporize and only vapor phase exists. So in vapor phase, I have my concentrations. Now let's have an overview about boiling point diagram. This is the boiling point diagram. You can see subcool liquid is first of all heated. That line AB. AB shows the heating process. We are heating the subcool liquid. Your subcool liquid, for example, can be simply take it as water at 25 degrees Celsius at room temperature. So that is a subcool condition. When it is heated up to B point. What happens at B point is my first bubble forms. Okay, means it is the onset of vaporization. Now vapors are also starting to form. So the corresponding line, that is, you can see the diagram from diagram BC. So at point C, the point C tells the composition of that component in vapor phase. Okay, moving forward. Now this is your boiling point diagram, T versus XY. Okay. Yesterday we saw your B point. Look at the B point. From subcool liquid. Okay, the subcool liquid means the liquid solution which I am taking. At B point, I am taking my mixture. XB is the concentration of benzene in liquid phase. It is 0.4. Okay. When I am heating my mixture from A, here in liquid phase you can see this is the condition of A. Okay. Total in liquid phase 0.4 and 0.6. Now from A to B I am heating it. So what line AB is, I am heating it. Suppose that I am taking the mixture at 25. Now from 25 I am heating it, and at point B. At point B, I have my liquid phase concentration as 0.4. Now it is the onset of vaporization. More volatile vapor will vaporize. Okay. So you can say because vapors are producing. Okay, now vapors are formed. Now the component which is more volatile, it will vaporize first. So I can say that my vapor phase is rich in benzene because my benzene is more volatile. Okay. Now continuing the line. At C point you can see it shows the vapor phase composition of benzene. Okay, because my benzene is more volatile, it will vaporize first, and the corresponding, the equilibrium concentration in vapor phase of benzene is given by C point. So at C point I can say that for my XB equal to 0.4, I get my YB, that is vapor phase composition of benzene, approximately equal to 0.8. So see, here enrichment has taken place. In vapor phase, you got more amount of benzene. Okay. See, the corresponding 0.8, it is the corresponding concentration of benzene in vapor phase. Now, if we condense this part of vapor, the vapors which I got, okay, from B point, when I heated my mixture to B point, and from that when I continued the heating, from the vapors which I got, then they were rich in benzene. Now if I condense this part of the vapor, and then it will get liquefied. Okay. Now I have liquid benzene with composition of 0.8. See, I have enriched my benzene now. So now on condensation of these vapors, I get benzene of 80% purity. So at 80%, now my new liquid solution, now my new liquid has benzene composition of 0.8. When I am reapplying the heat, when I am again heating it, then you can see the red line. Now corresponding to the heating, okay, I will get my vapor composition of approximately equal to 100%. So this way, VLE you can see the equilibrium between liquid and vapor phase compositions. So that was about when I was heating liquid to vapor. Okay. Now further, if we further heat the solution at point B, then after some time toluene will start to vaporize. Okay, I am continuously heating. My more volatile component, that is benzene, is separating out, vaporizing. But now toluene is also present. Okay, so as I am continuing the heating, I am increasing the temperature. Now after some point toluene will also get some of the energy and it will start to vaporize. Okay. So I can say that now in my vapor phase the concentration of toluene is increasing and the concentration of toluene in liquid is decreasing in vapor phase. Okay. Now this goes on till all the liquid is vaporized. So now benzene and toluene exist in vapor phase. So that was about converting liquid into the vapor phase. How initially a more volatile vaporizes, then followed by the less volatile component here, which was toluene, vaporizes. So this way the process goes on. Okay. Now similarly, if we condense this vapor, now for the initial slides you saw, when my total liquid is totally vaporized into vapor phase, now I have YB and YT. Now when I am starting my procedure of condensation, okay, now both of my components are in vapor phase. When I am starting the condensation process, initially benzene will condense first. Okay, why benzene will condense first? Because it is more volatile. Okay, so as I am decreasing the temperature, it will liquefy first. Now as liquefaction of benzene will occur, so my vapor phase would now be rich in toluene. Okay, so this way on condensation, less volatile component condenses first. Now what are the important notes you need to know over here? See, for pure component, bubble point, dew point are same and equal to boiling point of the liquid. That was discussed in last lecture also, that for pure component, okay, here I am not talking about mixture. Suppose for example take for pure benzene itself, its bubble point, its dew point and would be same and that would be equal to boiling point because here no mixing is there. Whereas the dew point and bubble point for a binary mixture is function of its composition. Okay, as we change the composition, for different composition you have different set of bubble point and dew point.